So orbital notation is telling us how many electrons there are in the electron cloud of a given element and in what sublevels those electrons are placed or exist in, and also in what orbitals they exist and in what spin orientation they exist. Okay, so it tells us an awful lot of information about the electron structure of an atom in its ground state. Ground state meaning the lowest energy state overall. Okay, so pick an element, any element. Come on, isn't that hard? There's only 117 here, actually 111 on this periodic table. Tungsten, okay. Boy, tungsten seems to be very popular today because that's the second time today somebody's picked tungsten. Not for this purpose, but for something else. But it was interesting. Okay, so tungsten. That's going to be a lot. Okay, tungsten. All right, so tungsten is way down here. All right, that means we've got to fill up all of the orbitals for all these elements, and including this whole row down here, because tungsten is 74. Notice that lanthanide stops at 57, and we jump to 58 down here with cerium. So this whole row has to go in right there. Okay? So that's what we're going to do. All right, so for tungsten's orbital notation. Now, let me say something about the test review system that I use, okay? There's some danger in this, because if all you're doing is listening, your chances of remembering what I have to say are really low. If all you're doing is listening, you're lucky to remember 20%. Now, if you want to make a 20 on the final exam, then just listen. But if you want to pass the final exam, you have to be more actively involved in that, okay? So if I'm going to do this on paper, it probably is really, really good for you to also do it on paper, okay? Because it's helping you to get it solidly in your brain. That makes sense? All right, so tungsten. We're going to start with the very first row, and hydrogen's here, and we're writing orbital notation. It's actually better if helium were placed here. It really could belong here or here. It doesn't really, in some sense, it makes more sense. And helium, we want to put it here because these two first rows, with helium included right there above beryllium, makes up the S sublevel region. And then all of this over here, minus the helium, makes up the P sublevel region. And these inner transition metals here make up the D sublevel region. And these, the transition metal area is the D sublevel region. The inner transition metals down here make up the S sublevel region. So it kind of helps you keep up with it if you know that helium belongs here. Okay? All right. So for the first two elements, hydrogen and helium, we've just got one orbital, and that's what the box represents, in the first primary energy level, and the designation we give to that type of orbital is S. That's the sublevel region represented by the first two columns. Okay? And so there are two electrons, one for hydrogen and one for helium. Now, the reason we have to put them as up arrows and down arrows, and I know I'll do a half arrow, it's just kind of saving time and space. The reason the reason we have to have arrows like that is this, that electrons have the same charge. They're both negative, have a negative electrical charge. Normally, you can't put two things with the same charge in the same region of space. They want to fly apart. But there's this funny thing that happens on the quantum level, down at the atomic or subatomic level, and it's called quantum entanglement. Well, to be simple about it, a little bit simpler than quantum entanglement, kind of like sounds really big. These arrows mean opposite spins. And if you have the electrons spinning in opposite directions, it's like you kind of cancel out the electrical charge that's making them repel. They're not really canceling the electrical charge, but they're canceling the repulsion part of it. Okay, without getting in too deep, that's what's happening. That's where we have the up and down arrows. And then, so now we're going to go to the second row of the periodic table, starting with lithium here. And lithium and beryllium are going to be representing where we have two more electrons, but now in the second primary level. So every row you come to on the periodic table represents another primary energy level. Okay, so this is two. This is the S sublevel region. So we've got two electrons, lithium and beryllium, there they are. And now we're going to go over here to where boron is, and we're in the P sublevel region. So this is still in the second row, so it's 2P. And over here we've got 1, 2, 3, 4, 5, 6 atoms, representing 6 electrons being added to an electron cloud. And since I can only put 2 electrons in an orbital, I need 3 orbitals. So here are 3 p orbitals. Okay? And so we're going to fill them all up because we've got to get all the way down here. So now what we're going to do is we're going to put 1 electron in each orbital and then come back and pair them up. All right? I like to call it the school bus rule. You know, nobody sits, well, you do if you know somebody, but if you're sitting on the school bus and you don't know anybody, you're going to sit on a seat by yourself rather than sit with somebody if you don't have to. Okay? And that's kind of what the electrons do. You put 1 in each orbital and then come back and pair them up. Okay? Now then, we filled up the second row. We've got to go to the third row. So we've got 3s and 3p in the third row. And we're going to fill those up, just like we did with row 2. 1 in each orbital, come back and pair them up. Now, something funky happens when we get to the 4th primary energy level, because when we get to the 4th energy level here, we start to fill up electrons in this section. These are the transition metals. These electrons that go into all these elements, scandium through zinc, don't fill up this 4th primary energy level. They drop back and put electrons down 1 energy level into 3. So instead of 4d, this is 3d through here, and then back to 4p over here. Okay? So we're going to fill up 4s, and then we're going to drop back to 3d. There are 10 atoms in that section from scandium to zinc, and so we need 5 orbitals. And we're going to fill those up, just like this. Now there is a kind of an exception that we get into when we have a nearly half full or nearly full D sublevel, where we pull an electron out of 4s, but we won't get into that today. All right, so that's 3D, and then we're going to go back to 4P when we get through with this transition metal area here. When we get to gallium, we're going to go back up to the 4th primary level and 4P, and we need 3 orbitals. 1 in each orbital, come back and pair it up. Then the 5s. 5s works the same way, or the 5th primary level works the same way. 1s orbital, and then instead of being in the same primary level, we're going to drop back 1, so this is 4d. Need 5 orbitals. 1 in each orbital, and come back and pair them up. And then we're going to get back up to 5p, 3 orbitals. Now I'm about to run out of space on the paper over here, so I'm going to go back to the next line, sort of a line under here, okay? We get to 6s. Oop, needs a little more space than that. 6s. All right, now. So right now, 1, 2, 3, 4, 5, 6. We're on the right row for tungsten. We're going to fill up 6s, so there's 2 electrons in 6s. And then we're going to go to 5d, that's where lanthanum is located. Alright, so here's 6s, cesium, barium, 2 electrons, and then we're going to the lanthanum. That's 5d. 1, 2, 3, 4, and 5. But we're only going to put 1 electron in there for lanthanum. Okay? Can't get it all in the same screenshot. Here we go. All right. 1 electron for lanthanum, 57 here. Lanthanum is 57, and this is not 58 here. From 57, we've got to go down here to the bottom where cerium is, and that's the F sublevel region. So we put 1 electron in to 5d for lanthanum, and then we've got to go to 4f. So we drop back 1 level for 5d, we drop back another level for 4f. And 4f has 14 atoms. That means we need 7 orbitals. 1, 2, 3, 4, 5, 6, 7. And this whole row down here gets filled up before we get back up here to hafnium. So 1, 2, 1 in each orbital. Come back and pair all these up. Now all these lanthanide series elements, they're really important to your computers and cell phones and smartphones and things like that. We have a lot of minute amounts, but a lot of these transition metal areas make all of our electronics really neat. Okay, make them work properly. Okay. So now we're back to we filled up the whole 4s sublevel. We're back to putting electrons into 5d again, where we get to hafnium. And between hafnium and tungsten, there are 1, 2, 3 more electrons. A total of 4 electrons in the d sublevel. 1, 2, 3, and 4. And there's tungsten. So alpha, that's a big element. That's a good choice in the sense that it helps me to explain all these sublevels to you, okay?